In 1977, Martin Gardner published the first article on fractals that featured Bill Gosper's flow snake curve, which was based on hexagons. You just saw a version of that. And what was amazing about it is that it was composed of just copies of self-avoiding congruent edge substituted motifs. So I thought to myself, well, why can't you do that for a square? And so let's do it. And let's take a square. We're going to take a distinguished edge. Here we'll take one of the four. It's the bottom. We're going to impart a direction to it. So if it's counterclockwise, we'll call it forward, and clockwise, we'll call it backward. So that each square has a parity equivalent to being inside or outside of a path. So that means each square has 8 possible states. Now we're going to subdivide the square into n squared subsquares. And we're going to define a Hilbert-style motif as a sequence of pairwise adjacent oriented subsquares from lower left to lower right, such that it's n squared long, includes each subsquare exactly once, and such that the distinguished edges form a piecewise connected path from A to B that is n squared long. Now, what I was interested in was, there's plenty of these paths, but you're interested in self-avoiding paths. And the problem is that, in general, there are 5 possible advances of this path at each vertex in this grid graph, which means the graph search algorithm is combinatorially explosive. There's 2 disjoint worlds for generalized Hilbert curve constructions. The first is where consecutive subsquares are only edge adjacent, and the second is everything else, where you can have adjacency that's corner to corner. And in my ebook app called Hilbert Curves, which I demoed at the last conference for the iPad, it explores everything in that first world, and you can learn lots of interesting, fun things there. But the rest of this talk is a synopsis of a paper I published 2 years ago called Fibbinary Zippers, blah, blah, blah. You can find it on the web just searching for Fibbinary Zippers, and it's about this other world that not a lot of people know about. So the Hilbert curve is the only solution for n equals 2 when you're subdividing into 2 by 2. And the top row there shows the distinguished edges in a motif that, when you edge substitute, unfortunately, they start self-contacting in the lattice. So the Hilbert curve doesn't solve the problem. Hilbert solved this problem by just connecting centers of adjacent subsquares, and that creates a self-avoiding path in the first illustration of a space-filling curve. Well, for n equals 3, there's only one solution, and unfortunately, when you iterate it recursively, it contacts in the lattice, so that doesn't solve anything. For n equals 4, there's 7 solutions. None of them work either. For n equals 5, there's 138 distinct motifs, and exactly one of them works. So if you take copies of this and plug it in recursively, it always creates a self-avoiding path on the lattice. And in fact, it's a Hamiltonian cycle on the toroidal grid graph at all finite approximations. So I discovered this by machine enumeration in 1978. It took an hour of CPU time on a PB20, and then I spent an entire weekend drawing it by hand because I didn't have any computer graphics machinery at the time. And then I was able to create a sequence of rotational analogs to it, and for any odd n, and I was doing this finally by hand and by plotter. And I wrote to Martin Gardner, and he said, well, you got to talk to Benoit Mandelbrot. Well, so I talked to Benoit Mandelbrot, and he offered me a job, so I ended up illustrating part of his book. So this is a plate you may recognize that was completely my work. And then I used their largest mainframe to search 6 by 6, and there were no solutions. That was kind of weird. I figured, well, if I found 1 for 5, there ought to be more for 6. Then I hit the combinatorial wall for about 25 years. And I had an epiphany for a better data structure, better pruning strategies, and faster PPCs. And so I was able to search 7. There were 7 solutions. They're all self-avoiding globally. One I'd found by hand back 20 years earlier. And I searched 8, and there were no solutions. So obviously there's something going on when n is even, or rather something not going on when n is even. I searched order 9, and there was 10,101 globally self-avoiding distinct motifs. And amazingly enough, they fell into two boundary classes, and they looked wildly different, and one class was a lot less than the other. So first I thought there was a bug in my software, or there's a phase change in the solution space. I didn't know what was going on, but I had to spend a lot of time figuring out what was going on and prove to myself that some of my assumptions were correct. So what's going on? Fibbinary zippers and frozen wedding cakes. So I'm going to skip over the proof, most of the proof, and get to the punchline. It turns out if you look at the left side of this n by n subdivision, the column of subsquares there are gaps. And remember, when you're recursively iterating this, whatever the shape of this path is, it's bouncing up against itself along the various grid lines. And there's a distribution which unfortunately is related to the shape of the path. So you have to look at the gaps along that where it gets close enough to itself, but not so close that it's self-contacting, and not so far away that it forces self-contact somewhere else. So these are called gaps. And on the left side, you can encode a gap by a 1, and you can encode everything else by 0, and a gap can't be next to itself. So you're talking about Fibbinary bit patterns, which is a set of bits n long where no one is adjacent to another 1. So the number of such bit patterns for a given length is a Fibonacci number. So it turns out that all of the combinatorial freedom for the left side is only in a small set of bits of n minus 3 over 2 bits. And they're all Fibbinary bit patterns, and they force the left side. So for n equals 17, there are only 13 boundary modes, and the rest of the paper is showing that the left side forces the top, the bottom, and the right side into the same set of Fibbinary bit patterns. And so the next interesting thing is that if you look at sequences of zeros, the longest sequence of zeros where there's no ones, it creates what I call frozen wedding cakes, where you get these alternating parity tiers of triangular shapes, and they all fit together, so that in fact, for mode 0, where the bits are all zeros, over half of the n squared subsquares are completely forced into an initial configuration before you even start the search. So here's for order 13. These are sample space-filling curve motifs, and you can see in the bottom row that they all work. They're self-avoiding, so you can fill them in. And for n equals 15, there's 8 Fibbinary zipper modes. So let's look at them all. Basically, we're counting in Fibbinary. So those are the 8 modes. And then for n equals 41, mode 0 looks like that. So the white area is basically a map of all combinatorial freedom in the problem. But if you have Fibbinary zipper bits where it's just 1, 1, it's equivalent to a Fibonacci number in the Zeckendorf representation of the integers, where you're using the Fibonacci numbers as a base instead of base 2. In any case, so as this 1 bit changes around, these maps are changed completely around, and the combinatorics are different. And I've been able to search the mode 0 for n equals 13 completely, so it takes 2 hours to find 34 million of them. But the rest of the modes are much more free, and there's a godzillion solutions. So I don't know whether I've hit the next combinatorial wall or not, but thanks.